Good morning, everyone. Welcome to the DDPS seminar. Before we introduce our invited speaker today, let's go over some rules as usual. First of all, please mute yourself during the talk. If you have immediate questions, you are welcome to unmute and ask. Or otherwise, please use the chat room to post your questions so that we will address your questions at the end in the Q&A session. Second, today's seminar is open to external audience, so no classified discussion is allowed. Finally, the talk will be recorded and uploaded to our YouTube channel. Now, let me introduce our speaker. It is an honor to host Mattias Chung, who goes by Tia. Tia is currently an associate professor in the Department of Mathematics at Emory University since 2022. Before that, he held faculty positions at Virginia Tech and Texas State University, and he was a postdoctoral fellow at Emory University. He obtained his doctoral degree from the University of Lübeck and master degree from the University of Hamburg, both in Germany. Tia is a Humboldt Fellow and an active member of SIAM. The focus of Tia's research is on solving ill-posed and large-scale inverse problems with applications in different disciplines, such as image processing, dynamical systems. He develops and analyzes efficient numerical methods with regularization, randomized methods, Bayesian inversion, and scientific machine learning. Today, Tia will present his work on big data inverse problems, promoting sparsity and learning to regularize. Please enjoy the wonderful talk. Now, without further ado, let me hand it to Tia by asking one random question. So, besides Atlanta and Savannah, what is your favorite city in Georgia?
In Georgia, Savannah. Savannah, or did you exclude Savannah?
Yeah, maybe excluding Savannah also.
Okay, so maybe Athens. I need to go then to Georgia State University of Georgia, which is a nice town over there.
Yeah, I heard that also. Okay.
Yeah.
Yeah, the stage is all yours right now.
Okay, thanks so much for having me, Tony, and for the introduction. I'm very excited to talk about some of my research with you, and I feel that can be also a discussion about some new directions. And I'm very happy if you interrupt me if you have any questions or comments throughout the talk. So I would be happy about that. So. Let me start here. Let's see. Oh, yeah, there we go. I wanted to start with a little bit more of my introduction. So first of all, here in the front, you see Emory University, and in the background, you see the skyline from Atlanta. So that is a pretty city as well. And I'm sitting right in this building here with the observatory over here somewhere at the side. And of course, it's not fall right now, but very green, light green at the moment. So Emory University is nicely located close to Atlanta or in Atlanta. And yeah, it's always nice to visit that place. All right. As Tony already said, so my work is somewhere in the field of inverse problems, scientific machine learning, UQ, dynamical systems, all involved. And I just made it a little bit schematic over here. So in the intersection of these methods, nevertheless, central to all what I'm doing are two major things, and that is a model and data. And with that, I think I fit somehow within the theme of the seminar, which is data-driven physical simulations. So what I'm particularly interested in is inverse problems. So here I did a very simple sketch of what are data-driven, or what I assume what is data model-driven. If I have just data given, my model-less information could be just a line, and I cannot extrapolate information out of this regime where my data give me good information. On the other hand, if I would have just a model, the model lines could go lie everywhere where I don't have any proper information. However, both together might give me good predictions for future events or for things we haven't observed. So this is a big regime, and today I want to talk specifically about inverse problem and how better to illustrate this with some images. And I give here just a simple image deblurring example. This one here, let's assume that is our true image, and let's assume we have some blur in there, and we assume this is done by some forward operation, maybe some Gaussian kernel, and we get a blurred image. And the actually interest is coming from a blurred and noisy image to go back to the true image. So we can write this down as a linear problem, and we have done that many times before. Going the opposite direction is essentially just inverting the operator, and we should get back our image. If we were to do that here in this example, that leads to a total failure of recovering the information we actually want, although I have the true model in there. So what happens? So the part of inverse problems is that it is ill-posed, meaning noise in the data or in the model or in the numerics, even though, can be amplified. So, and that is summarized by the notion of ill-posedness or ill-conditioned of an operator. And we say a problem is ill-posed if a solution does not exist, is not unique, or does not depend continuously on the data. And that goes back to Hadamard, who we are seeing here on the very right. All right, that is more the stage of inverse problems, and illustrated with some images. We can write this in many different forms, and I don't want to take the Bayesian approach. I will here just look at the variational approach. We typically have a data fidelity term or loss function between the model and the data. And to stabilize the data fit, we need some prior knowledge, which is encoded in typically some regularization. And this regularization might depend even some hyperparameters, which are imposed, regularization parameters, or in your Gaussian, or if you have other distributions where your regularizer comes from some other terms which might influence your prior knowledge, which you want to induce into your system. So as we've seen earlier, just looking at the data fidelity term might lead to an ill-posed problem, and we need the stabilization. A standard example here is the Tikhonov problem, where we have a data fidelity term over here with some regularization term where we want the solution to be close, somehow in some sense to 0. That is the standard setup. And of course, we are doing this for many years, but where are still the challenges? And one thing is definitely the dimensionalities. If we think about training a neural network as an inverse problem, is definitely the dimensionality involved in that. Or if we have reconstructions of some medical MRI images which are four-dimensional, then this problem goes fast out of hand, and standard methods do not necessarily apply. Another thing which I already talked a little bit about is the regularization. It's how do I include this? For example, how do I pick a regularization parameter? This is a priori not necessarily known. It is sometimes derived from the noise distribution of our problem, but that is not necessarily there. And the last thing is probably the uncertainty quantification. If we want for large-scale problems also to know a little bit about how certain we are about our inverse solution, then this one is typically computational, very expensive, and this is a challenge to work on that. All right, I will mostly talk about the first two parts, and for now, at least, ignore a little bit the uncertainty quantification, but although it is a topic on its own. All right, more specifically, I will talk about a new project, a new method we developed, and this is what we call variable projected augmented Lagrangian, and I will get into a lot of details over there. The archive paper you can find over here. We're lucky to get some funding, and I want to acknowledge NSF there, and this is a joint project with Rosie Renard and Petra Streneas. All right, let's dive into that and look at the following. I want to solve the following inverse problems. Here I have a data fidelity term, and you see I for simplicity, I'm looking at a linear problem and some regularization term. And you saw Tikhonov regularization has a 2 norm squared. Here we look at a 1 norm. And some matrix D over here as well with a sum operator, which we want to project our solution onto. And typically what we want is sparsity in our solution. And L1, L0 type norm is not suitable or computationally too expensive. We use the L1 norm over here, which promotes sparsity in general, as the RIP condition is satisfied and so on. Nevertheless, we have done that many times, and this is typically referred to as a generalized lasso problem. The generalized comes through an operator D, otherwise we just call it a lasso problem. All right, and some regularization parameter over here. All right, so to give you an example where these type of problems come up, and this is definitely a single signal processing, more specifically signal compression, where the signal needs to compress and you want a lot of pieces to be zero, compress sensing, and you already see these are all topics which came up, especially in the late 2000s and started 2000s. Dictionary learning is something else, but also denoising, image deblurring, and other things. I will talk about a couple of potential applications. It's a wide variety which we can look at. So this generalized lasso is computationally expensive, since we need iterative methods to solve these problems. We cannot directly solve it like the Tikhonov problems if we have not too large problem, and we can just invert. But here we typically need an iterative method, and it is computationally more challenging than, for example, the Tikhonov. Then the point I already made, also here, we typically don't know the regularization parameter. How can we determine this parameter, especially in the sense or in the settings of L1 regularization, which is not standard? Many tools have been developed for the L2 norm for the Tikhonov problem. For the L1, it is a little bit harder. Of course, there is a zoo of methods out there to attack this generalized lasso problem, and I stated a couple of methods over here. And if you want to, I actually put one more animal into the zoo, but I want to convince you that there is a good reason to use these kind of methods. All right, to start with, I just want to be on the same page that everyone can hopefully follow. I want to introduce ADMM and derive it and just see how we develop the variable projected augmented Lagrangian. All right, let's keep going. So this was our problem over here, and we can reformulate this by introducing just a surrogate variable here, the y, and what we do is we are just enforcing the y to be equal to dx. We are just replacing this piece. In general, that might be a bad idea. Everyone who has some optimization will say, okay, a constrained optimization problem is significantly harder than an unconstrained optimization problem. Why would we do that? We will get to that. So the first thing you do is, okay, I have this constraint problem. I form the Lagrange function and include also a penalty term. And this is the quadratic penalty term where we call this the augmented Lagrangian. Here I have my Lagrange multipliers over here, and this is my augmented Lagrangian where I not enforce it strictly, but have some penalty term when y is not equal to dx. And you see that the last two terms are some quadratic terms, and we can reshuffle these both and just reformulate this both together to have it in this form, which is easier to handle. And then the C takes the form of our Lagrange multiplier with some factor over here. Of course, the lambda over here is an additional penalty parameter, which penalizes our nonconformity to our constraint. All right, this is augmented Lagrangian. And before I start talking about ADMM again, I want to scale back and say, let's look at a generic function. And for simplicity, let f be strictly convex. And I want to assume it's separable, meaning I have two sets of variables which have different meanings or which I can separate. You can think about, if you are familiar with a lot of training neural networks, each layer has a set of parameters, and they have different meanings. They are interacting, but they have different meanings or might live on different scales, right? Or you may have some linear parameters and some nonlinear parameters. How can you solve these kind of generic problems? So actually what we have seen is we just artificially introduced a variable in our previous slide. So this one can come through reformulation of a separable problem, or naturally appearing in applications. And one example is super resolution, where you have a lot of small images and you want to reconstruct a larger image with sub-pixel information. Let me tell you what we could do. So the first approach is just ignore that we have two different variables, right? And just combine them both together and take your favorite method to use an iterative optimization method. Maybe that's some gradient descent method, or some BFGS, or whatever optimization method you want over here, and you want to minimize that. Let me go back, sorry for that. This is one approach. That oftentimes suffers some slow convergence, especially if the variables are on different scales or have very different meaning. To combat this, there are typically two approaches which you can use. One is coordinate descent. What you're doing there is you are taking your favorite optimization method again, going in one direction a step, and then in the other direction a step. And you're continuing this process over and over again. And there's a third approach, which is called alternating direction. And the alternating direction, instead of going a step in a direction, you're optimizing in this direction, and then you optimize in the opposite direction, and you continue this approach over and over again. So, and I think with this last illustration over here, we are very close to our ADMM method, alternating direction. We had two variables in here, and we are alternating essentially over these variables. So that is ADMM essentially. You have an update on your parameter X, minimizing this problem over here. Then you update your Y, minimizing this problem. And the Lagrange multiplier, and I don't want to say too much, that you can update them as well. instead of increasing the penalty parameter, you can use this approach. So now let's digest this a little bit and what just happened. So first of all, we have here suddenly a linearly squares problem. Since our y is constant, this one is now easy to solve, right? We know we can solve a linearly squares problem. Since y is constant, that is perfect. Wonderful to do. The second thing is this guy over here. If you look at the y, it goes in here and here, and it is not convoluted by a matrix, means all these optimization problems are independent, first of all, and it is the so-called shrinkage problem. So we can actually have an analytic solution for that by this it's not complicated, but an easy update formula. Okay, details we don't need to know about this, right? But this is fairly straightforward then to do. And then the last part is the Lagrange update on the Lagrange multipliers. So if we look at this method, where is the computational most effort we need to put in? That is, of course, the first part over here. There I have some matrices A and D, and I need to solve this linear problem. So if I take a standard method, so it will be somehow of the complexity of some, however many iterations I took in my auto iteration times the dimensionality times n squared, somewhere around this. But of course, since line 4 is the most expensive one, we typically do an iterative method to solve this, and we don't even potentially accurately solve that, maybe go just a couple of iterations, right? Another way is to do decomposition of these matrices beforehand, because you're always applying the same matrix, so you could do something like a Cholesky factorization if you consider the normal equations, right? Something like that. All right. So so far so good. That is ADMM. But I didn't tell you that there is actually a fourth option of what we discussed earlier. And the fourth option is the variable projection. Before we did optimization, or update step, or ignoring, but you can also hibernate this. Update in one direction and optimize in the other one. And this is what we call variable projection. And we can actually write it in this form, like I showed over here, an update just of x, and somehow eliminate the second variable within the first variable. Okay, so this one was actually developed in the early 70s by Golub-Pereira, and that was particularly for the separable nonlinear problems where you have A of x, where x is a nonlinear operator or nonlinear parameter determining your operator, and y is a linear variable. So for this, it has been developed. And we could easily apply this also for the generalized lasso approach. So all we need to do is changing line 4, where we do an update on the linear problem and then solve for the second one. I want to just to emphasize over here that we do it actually opposite to what the variable projection was intended to, and that is updating the linear and optimizing over the nonlinear, because the nonlinear is actually straightforward. So this is what we call then variable projected augmented Lagrangian method. And if you look at this, did I have it over here? I think I might have put it in the next slide. This is a projected problem over here, and several nice things happen to this update. It is, if I compute gradient information, the nonlinear problem goes away because we have optimality. So a lot of computational pieces will get easier. Here you could, for example, take as the step direction the negative gradient, right? That would be one option, but there are other choices, right? And this is just one of them. I also could compute a line search parameter. Actually, I could, for simplicity here, just use the linearized line search parameter, the optimal linearized line search parameter. And then it would be something like a conjugate gradient step, just one conjugate gradient step in my linear problem. And the computational cost, if I'm looking at this algorithm, it just reduces here from n squared to n. That is what the difference is. And since we are now in the realm of standard optimization method, I could use any optimization method to use for my search direction. And standard stopping criteria you can impose on this unconstrained optimization. All right, so I think it is good time to first look at an example how this works. Let's see that. Or I just summarized everything again over here with a particular choice. This is just the simplest choice I can think of to make it work. The nice thing is about there are just matrix vector multiplies. There's no inversion in there in the algorithm. It is very straightforward. So there's no LSQR, which I need to pack in there like with ADMM and so on. This will just need per iteration 2 matrix vector multiplies with A and B and 1 transpose, so 1 adjoint for that, for each. All right. Before I show the numerics, just a quick, and I put a couple of things under the rug, but we can show that if we use the variable projected augmented Lagrangian method, then we can show that the method will converge. There's uniqueness. We need to show uniqueness of the projected problem. And then we need to show that the variable projection method converges, and then later on that the augmented Lagrangian method converges. And we are coupling all of these elements together then into one. All right, so now we have time for some numerical experiments. Let's start with a couple of things. First of all, this is a denoising problem, the simplest what we can think of. So the operator A is just the identity, and the D operator here comes from a total variation, meaning what I actually want in the derivative in each direction, I want just a few jumps, right? And that is what the D operator does over here. So it's a 2D total variation. We are comparing to ADMM. There we use LSQR for the inner solve. And here for just illustration, we pick a regularization parameter 10 and a standard stopping criteria 10 here, more 10 to the minus 4. And let's see how both of these methods perform. So here on the left, you see the iteration count and the residual over here in a log 10. And here is the error over here. So what you will see is that the residual and also the errors go nearly to the identical values. The relative errors are nearly identical. But what you see is ADMM uses less iterations than we use. However, this is an arbitrary count, right? Because what does iterations really mean? So we want to look at what is the actual work we are doing. So we are looking at the wall clock time. And there the picture looks very different. If we look on the left, we are looking at sizes of this image and just increase the sizes. And we also compare to a Tikhonov solution. Of course, Tikhonov is just a linear inversion and the time is very fast. However, the reconstruction will be terrible because that is not, we don't want an L2 regularizer over here. And if you look at the wall clock time, the blue one, the V-power variable projection method is significantly faster. despite they both produce essentially the same image. The curves of the relative error lie on the same path over here. And if we look at the timings over here, how ADMM versus VPOL looks like, it is between 7 and 9 speed up. And I also looked at the number of matrix vector multiplications which I needed within ADMM or VPOL. That was already encouraging. Let me show you another image over here that came from the beginning. The girl with a tall earring over here, and what I just did, I did an inpainting example, and this is essentially an indicator function which we have over here. And what I did as a small test is what happens when I change my regularization parameter to my timing and to my relative error. And you see, if I take a small regularization error, then my timing is very bad. And if I take it too high, it will be bad as well. But where I hit around about a good reconstruction, the method is fairly fast. So that shows the importance of a regularization parameter. But how do I select this regularization parameter? And there are many different methods already out there, as I mentioned. Discrepancy principle, UPRE, and generalized cross-validation. They are all methods which we can utilize. However, they get a little computational expensive, and they don't generalize to the L1 so easily. More needs to be put in there. What we took a different approach. We said we want to learn the regularization parameter. So what we assume is there is a mapping from our observation to our regularization parameter. And I put this boldface here since we think about this not only as a regularization parameter, some hyperparameters or some information about your prior. You can construct a neural network which you parameterize to approximate this mapping. And you learn this mapping. And here I just, for completeness, I just wrote down a neural network, but I think I don't need to, in this crowd, go through many details there. You know what a neural network is. You're mapping from B to the regularization, and it's parameterized with all the weights and bias terms. And you want to learn on the parameters in this network to get a good mapping from B to the regularization parameter. That means once I've learned this, a new B I'm getting, I just need to forward propagate through my network and get a regularization parameter. Just some details on how we pick the loss function and so on. And let me just summarize what we do. The learning is the offline phase. We generate some training data, some B, and some optimal regularization parameter. We can do that since we are in the training phase and we know the underlying truth over there. Then we set up the neural network and learn the neural network from this data. In the offline phase, we get a new B, propagate forward, and then we can compute the inverse problem. So notice here, I don't want to throw away the physical model, right? I'm learning just on the prior. I don't learn the mapping from B to the reconstructions. I want to still have the physics in my system, but I want to induce information on my prior. All right, here is a simple example for a heat equation, 1D heat equation, just proof of concept. And here I looked at the Tikhonov problem, generated a bunch of random signals with some noise, and I even chose different noise levels, right? With this, I can do this however I want. I compared these methods to UPRE, GCV, these are standard methods, and discrepancy principle I cut out because otherwise you wouldn't see anything in the pictures that underperformed significantly. There's another method which is on the optimal experiment, comes from optimal experimental design, And then I use two different neural networks. One is a DNN and one is an LRM, or extreme learning machine, which is just a linear network essentially, without activation. So, and we learn on some training data. So let me show you the results over here. On the left-hand side, we look at a test set and we look at the difference between our recovered parameter and the optimal. And I use all these different methods. This should be an IOID, sorry for that. And of course, it should be around 0. That would be optimal, right? So to hit the optimal parameters. And you'll see the DNNs perform extremely well over here compared to any of the statistical methods or to the linearized model. If we translate this in the reconstruction arrow over here in the right-hand side, you will see this is the optimal I can do in the black over here, and I can zoom in, and you see the DNN pretty much capture it very well, right? Okay. That is good. All right, so disadvantage of standard method is that it is very expensive to compute the regularization parameter, and it is not always optimal, but you don't need any learning process within that. While DNNs and OIDs needs learning to generate your regularization parameter, but the DNNs perform extremely well and are adaptive to your data. Once you get a new data in, you get a new regularization parameter, especially for these data which I was presented at. I took one more example from tomography over here, which is also a linear operation, and I slowly curve back to the generalized lasso problem. Let me go back. If you are not familiar with tomography, you essentially have a source and a receiver over here, and you're having line integrals, and you compute the attenuation coefficient, and you are essentially put your data in one line you observe over here, and then you're rotating and you put all the data on here. But from this, we call it sinogram, you want to reconstruct the image. And this is the Shep-Logan phantom, and there are randomized Shep-Logan we use to training this data over here. The setup is as we had before with some noise levels, and I don't want to go into the details, only that we use a regularization now, which is the generalized lasso problem, where we cannot so easily use standard statistical methods to estimate the regularization parameter. And here are some test images or training images we have over here. And let me just do quickly the DNN setup. Of course, we are operating on images, so we are talking about convolutional neural networks, makes the training easier. Small note on that, actually training this network to the regularization parameter is extremely easy. You're going to one dimension. This is not a large dimensional problem, right? You're going from a large dimensional to a one-dimensional problem, which is a piece of cake for these neural networks. Okay, that is all set up. How we learn, we do use Adam and mini batches with a certain learning rate over here. And I look at the two different DNNs, the DNN and the shallow network over here, and you see the optimal regularization parameter compared to the true, the optimal compared to the learned regularization parameter. And if this one is around this line over here, it would be best. And you see that DNN does pretty well. The LRM cannot learn so well because it's a linear mapping. You might get even negative regularization parameters, which in this case is not of any value. Okay, so how does now the performance look there? If I look at the distribution of my discrepancy between my learned one and the optimal one, I see I'm very well, perform very well with my DNN. Looking over here with a relative error and the density over here, the optimal is highlighted in black, and the DNN, I think we can ignore the linear neural network. It performs pretty well. And I want to point something out which I was surprised about, and that is, why is our neural network better than the optimal one? That cannot be. And I, at a certain point, noticed that the optimal regularization parameter I numerically solved. And in some cases, it didn't find, it was in a local minima, and it never found the optimal one, while the neural network was able to compensate even for that, which was very impressive. Of course, we did a lot of other experiments. For example, took total out of sample images, which generated still very good results. All right, I'm circling back to a couple of applications to give you some time or give us some time for discussion. This is a very exciting recent work. We are working on 5D MRI, cardiac MRI, and if you ask me what 5D MRI is, I don't know what the 5D actually means here. It sounds strange, but it comes not from me, okay? The point 5D means actually it comes through two different phases, the respiratory and the cardiac, and you want to reconstruct a 3D volume in time with the respiratory and the cardiac phase. And this was a project we just recently started, and we looked at ADMM, which they standard used, and we just implemented VPAL on a very small scale. And this is the timing from 14.4 hours to 4.5. And that is just the simplest form we could do. That is just the starting point. And if you think about, you want your results of a cardiac image very fast, 14.4 hours is not reasonable. But 4.5 goes already in this right direction. Nevertheless, in the beginning, I showed you a speed of 7 to 9. We are not there yet. So there's still something to do. There's also other tool methods we can use, or undersampling, where we are now not yet. Nevertheless, the sizes of the problem are extremely large, and data size is extremely large, and these methods are performing pretty well on this example. A question I often get is, where is the difference between variable projection, augmented Lagrangian, compared to ADMM? And an ADMM where you don't solve all till the very end. Actually, we never do this, right? You have an inexact ADMM, and that's what most people are using. However, in ADMM, the Y is always fixed in the first problem to optimize over X or to find an X. Here, we don't need this. Here, it is adapted because we are on a different manifold. And this I just illustrate by using, for example, a linear, different regularization, different step size, different learning rate over here, which is not just the linearized one. If I choose that, I go to the convergence much faster over here in just 40 iteration or 30 iteration compared to 120. While the step length is significantly different. So the methods are really different. There you are operating on different manifolds. Because there are so many applications, I want to just show you some I played around with, which are just fun to do. And this one is, for example, graph trend filtering where with missing data. So you have here, for example, the road map of Minnesota, and you have some trend in the data, and there are some missing black dots, and you want to reconstruct this information of the true data. And you can do that via L1 regularization. Here, the operator looks a little bit different than just the standard finite difference one, but it is fun to play with these kind of problems, and they are solved very fast. Here's another problem which I mentioned already in the beginning, so which is super resolution. You have a bunch of small resolution images, and now I put Tony on the spot. What do you think what is this? Can you identify what the image is?
Be an astronaut.
Yeah, exactly. That's an astronaut. And if you actually do this pixel information and you do the reconstruction, this is the true one, and this is the reconstruction I'm getting with VPAL over here. I don't know if I have another example. Oh, I have one more, but that is already in my conclusion. I think I finished up hopefully about in time. So my first plea is variable rejection is underutilized, and it is fun to play with that and can give surprisingly good results in many different ways. We used it also in training neural networks, separable neural networks, which I didn't talk about today. But if you are looking at some sparse recovery with some lasso problems, VPAL has some fast convergence. Of course, this is just the beginning of things we are investigating. One thing is, so far I talked about linear operators. Nonlinear operators, we don't need to change our code. Our code works for nonlinear operators as well, but we haven't played with that as well. So if there are some nonlinear PDEs involved in that, that would be very interesting. We just last week tried to do dictionary learning. Here you see the first results. Actually, I have already better results. So we ran it already twice and did some dictionary learning, but more to come in the future. I didn't talk much about changing the norms. You can do this with this separable function as well. If you are separating or the splitting of the variables, you can leverage. There are some points as well. My collaborator works on joint inversion at the moment. If you have two different modalities and you want to join this information, for example, in subsurface imaging, we are doing that right now and looking at some results over there. I talked very briefly about convergence, but there's still a lot more to do. And where I want to go, and I spent some time on randomized methods, I want to include them in this framework as well, so that we can go to larger dimensions even than we are doing right now. I talked a bit about the selection of the regularization parameter, but there is still lots to do. It depends a little bit still on the operator. How can we get information out of that? That's also something we are currently working on. And I just showed you the simplest version of VPAL with a certain descent direction and step size selection, but we can generalize this and we can use different things. We already started that as well, and it works fine, but there's still a long way to go. And with this, I'm happy to take any questions. Thank you, everyone.
Yeah, thank you very much, Tia, for the wonderful talk. I believe everyone enjoyed Tia's talk as much as I do. So now is the Q&A section, so please feel free to unmute yourself and ask questions. Yeah, maybe I can start by asking you a question. So I'm curious about the neural network approach for getting the regularization parameter. So I can see that getting the parameter in the online phase is cheap, but in the offline phase, you have to solve for the optimal parameter. So how expensive is that labeling process actually?
You hit the nail on the head. You know, that is the expensive part at the moment over here. training the neural network is a piece of cake.
Yes.
Really, that is the easy part. But finding the optimal parameter is not necessarily even convex problem. And we went already in some directions that is reinforcement learning, that we are learning it on the fly what a good parameter is. Not the optimal, but ignoring what the optimal is, but trying to reconstruct the image of the optimal parameter. So trying to ignore that one. However, so far that is also computational expensive, and reinforcement learning is not really prone to converge very fast. So that is something we are working on right now, but good question, very good question.
I see. Yeah, thanks for the answer. So, is there a question from the audience?
Yep. Yeah, thanks for great talk. I'm PhD from UT Austin. So I just following the single questions. I just follow that, and I think there is a paper that people, the author, they train the trainable parameters in the inverse problem framework. They train the regularizer and regularization parameter at the same times, and they achieve a better than the normal taken up regularizations. I mean, in that work is like not only train the optimal regularization parameter, but they also train, I think, the inverse map at the same time. So
Yeah,
I just mentioned that, so you can take a look on that and make comparison.
You are talking about 10x10's work on that?
No.
No. Okay. So there is some work on there as well, and what we try to avoid over here is learning the inverse map from B to X. Then that is the inverse problem, and I know that there's tons of work out there, and it's very interesting. But we wanted to keep the physical model really in place. We didn't want to touch this piece. But you're right. There's a lot of interesting work out. Nevertheless, whatever paper you have there in mind, please send it to me. I'm very interested about developments which are there.
Sure. Yeah, because what I have in mind is, like instead of we just waste a resource to train only the regularization parameter, right? Learning like the approach learning regularizer, they also have the same meaning. Like they include optimum regularization parameter with the prior like the proper regularizer for the inverse problem. So we have the like one kill two birds, something like that, instead of only regularization parameter. I will send you later.
Yeah. So to be honest, we that's why I did it a boldface. So we learned not only one regularization parameter. We did multiple different things. One thing is, for example, what we learned, which was interesting, how many iterative solves I should do in my inversion process, because that is, for example, implicit regularization, right? So that I have my B and I will get how many iterations when should I stop with my iterations, right? Other things is, for example, you might want to have a mean or some covariance information, right? So you want parameterized covariance, or so you want to maybe learn that one. Yeah, these are all different options, which is really great, and we haven't explored everything yet. But I'm really very curious. Please send me the paper or the link to the paper.
Yeah.
Thank you.
Yep, and yeah, I just like one more thing that like you mentioned about big data inverse problem, right? And then if we have big data and we need to do find the optimum for training data, I think is very expensive. Right?
Yeah, so there's some work we did on iterative, so it's on sketching, iterative sketching. If you have your large and you just use pieces of your data, and there's a relationship between the sampled regularization parameter, the regularization to the sampled problem to the overall regularization parameter. And if you're doing iterative selling, you can actually learn the regularization why you're going, which is very interesting. And we applied this for linear problems. This is called SlimTick, sample limited memory Tikhonov, or then for neural networks, this is called sample limited memory training, so SlimTrain.
Oh, do you have that work on your Google Scholar?
Yeah, it should be. It's called, if you look SlimTrain, then you will find it. I hope so.
Okay, thank you. Great.
Yeah, sure.
Yeah, thank you so much.
Okay, so we get some fruitful discussion. So are there any more questions from the audience? So if we
Hi, Tia. This is Ying Liang. I'm currently a postdoc at Purdue University. Thanks for your wonderful talk. My question is related to, can you maybe turn to page 23rd or somewhere? You have a figure showing the how the accuracy will change with respect to the choice of regularization.
This one here?
Yes, yeah, this
Okay.
figure on the left top.
Mhm.
Or right top. And I'm wondering that for the data-driven case, we actually have the noise model, right? So we have some principles that we can actually choose a relative okay parameter mu, right? So maybe not an optimal for each measurement, but it's an okay one. So my question is that, will the reconstruction be quite sensitive to the choice of the mu when it is near this relative good regularization parameter?
That is an extremely good question, right? And first of all, I want to answer it. It always depends on the application, right? So how sensitive your regularization parameter is, right? We see here, for example, their regularization parameter between 10 to the -4 and 10 to the -2. It will give me the pretty much the same result, right? But if we have a good method to just a priori estimate it, plug it in, right? That will definitely help. If I'm looking though at the discrepancy principle or UPIE or generalized cross-validation, for large-scale problems, they're extremely expensive because you need to invert this system multiple times. Right. So, and that becomes very expensive. And that's why we are currently working on using the DNNs, particular for this problem, but also including information about the operator, so that not only B, but also the operator, just some small information is in there that we can have a quick information about the regularization parameter. And you're right, maybe additional information, maybe noise variance. If I know that, I should plug it in, right? I can get out, there's something out, and I would love to include that, yeah.
Okay, thank you for your answer.
I just like have the following comment on this one as well. There is a active subspace methods for inverse problems. So if actually I did research on that, and if we apply active subspace or inverse problem here, so we will for large like over regularization parameter, we will still get a good results, like the active space will robustness with the over regularizations parameter. So you will not have the inaccurate go blows up on with the large regularization parameter.
Maybe I don't follow. Are you saying you want an iterative approach to just use large singular values essentially to reconstruct, or do you want to? Yeah.
Yeah, calibrate that. Yes.
Yeah, that would be an iterative method in there, but that is typically more for L2 regularization. For L1, it becomes a little bit more difficult, right?
Yes, I agree. Yeah, thank you.
Okay, so if there are no more questions, let's thank again Tia for his wonderful talk and sharing his excellent results of us. Okay, I
Thank you,
will
everyone.
stop recording here.